In this past semester, I've had the pleasure of working with Dr. Kasra Momeni through the Department of Engineering on our research, the design for in-space manufacturing of metallic components. So this evening, I hope to give you a brief overview of our research by discussing the background of our research, as well as the potential alloys that we have been looking at this past semester, and our future plans for our research. So what is a background of our research? The specific form of in-space manufacturing that we have been looking at is in-space welding. A little history on in-space welding. There have been 3 attempts at in-space welding throughout all of human history. Firstly, in 1969, the Russians went up and proved that traditional welding is in fact possible in a semi-atmospheric environment. Not to be beaten, the Americans also went up in 1973 and proved the same thing. They also proved that brazing was possible in space. Brazing is the form of welding that you think of when someone just says, think of welding. It is the fusion of 2 pieces of metal together using a filler wire and a shield gas to maintain the quality of the atmospheric environment. And by doing this, the 2 pieces of metal are liquidized and form something known as a weld pool before it solidifies back into 1 piece of metal. And finally, in 1984, possibly the most important form of in-space welding was attempted. It was proven that you could in fact weld in the vacuum of space. Now, the uses of in-space welding are only becoming more prominent as we continue to push out in more deep space missions. The large-scale constructions will become possible as we continue to push out into deep space environments, because we will need to establish bases out in space and on the moon to be able to manufacture the tools and resources that we will need to continue these deep space missions. Additionally, we will need to be able to repair and maintain any materials that we do send out into space. Because these missions are going to be so long, it is no longer possible for us to just patchwork these problems that come across. We will need to find ways to permanently repair any problems that we are facing. However, there are quite a few challenges that we encounter when we are trying to weld in space. First and foremost, the vacuum of space. Because we need a shielding gas for traditional welding, it becomes really difficult to maintain that atmospheric environment within the vacuum of space. Secondly, the microgravity environment of space causes the weld pool that is formed in traditional welding to behave in a way that is different to what we're used to on Earth, which affects the quality of the weld overall. And finally, the extreme temperature differences, both hot and cold, that are encountered in space cause the quality of the weld to decrease as a whole. So the specific form of welding that we will be looking at is friction stir welding. Friction stir welding is a relatively new form of welding that doesn't look like traditional welding at all. Instead of using a filler wire and shielding gas, it instead uses a shoulder and pin joint, as you can see in this video, and it rotates at a very high rate of speed as it inserted between the 2 pieces of metal, similar to a drill bit. This friction that occurs between the pieces of metal and the pin joint causes the 2 pieces of metal to almost liquidize, but really more like soften and fuse together into 1 piece of metal. This process is currently used primarily with aluminum-based alloys, and it is also primarily used in the automotive industry, the shipbuilding industry, and primarily the aerospace industry. It is exceptionally beneficial to us when we are considering in-space welding because it does not require a filler wire, which means that we do not need to bring in additional materials into space. It does not require shielding gas, which means it can be used in the vacuum of space, and it does not form a weld pool, so we don't need to be as concerned about the behavior of the weld pool in a microgravity environment. So the programs that we have been using to evaluate our friction stir welding model is ThermoCalc and COMSOL. ThermoCalc is a thermodynamical program that allows us to come up with the thermodynamic properties of our alloys that we have been looking at. It does this by allowing us to put in the exact percentages of the elemental makeups of our alloys into the program, and it gives us the values that we need. We need three variables from this specifically: thermal conductivity, specific heat capacity, and density. Taking these variables, we then plug them into our COMSOL model. Our COMSOL program allows us to actually model the physical effect of the friction stir welding and the temperature effects that it has on the alloys while it is going through this stress. By plugging in these 3 specific values into our COMSOL model, we are able to model the alloys as close to the real-life equivalent as possible. So what are the potential alloys that we've been looking at? We have been looking at 2 potential alloys primarily. Firstly is aluminum 2219. Aluminum 2219 is an aluminum alloy made up of aluminum and copper, and it is very commonly used in friction stir welding, which is why we're primarily using it as a baseline for our research. It is very commonly used in the aerospace industry as well, primarily because it is incredibly resistant to stress corrosion, which is useful when you're putting it through the extremes that it takes to put things into space and also maintain the extreme environment that is space. Additionally, it remains incredibly durable at a long range of temperatures, both hot and cold, which is useful when you're dealing with the cold, dark vacuum of space, and also is incredibly easy to weld. The second alloy that we have been looking at in our research is INCONEL 718. INCONEL 718 is a nickel-based alloy that is primarily made up of nickel, chromium, iron, and niobium. It is also very commonly used in the aerospace industry. It is primarily used for rocket engine parts, gas turbines and pumps, anything that has a gas or a liquid flowing through it. It is used for this because it has incredibly high strength at a large range of temperatures, similar to aluminum 2219, and is also incredibly corrosion resistant. So these are the COMSOL models that we have currently created for both aluminum 2219 on the left and INCONEL 718 on the right. So as you can see here, the little blue half circles that you see in the center are where our shoulder and pin joint are inserted into the metal. It rotates at such a high velocity that it causes the pieces of metals to soften. And as you can see in the models, the temperature tends to spread outward. So what we are looking at in these models currently, since they're being modeled for an Earth atmosphere and environment, are the metals behaving in the way that we are expecting them to. So with the aluminum, you can see that the metals tend to spread out a bit more. The temperature tends to spread. It's more evenly orange across the whole thing. While for the INCONEL, it seems to be incredibly self-contained. It almost is a strip of just straight white. So that is what we are looking for because the temperature spreads more of aluminum and not INCONEL. This makes sense because INCONEL 718 has a much lower thermal conductivity than aluminum 2219, which means that INCONEL 718 tends to act as an insulator, while aluminum 22 does not. So that representation means that our model is working effectively. Additionally, you can see that the temperature range for aluminum 2219 goes up to about 900 degrees Kelvin, while for INCONEL 718 it goes up to about 1400 degrees Kelvin, significantly higher. However, this is exactly what we are expecting because the melting point for each of these metals for aluminum is roughly around 900 degrees Kelvin, and for INCONEL is roughly 1400 degrees Kelvin. So the fact that it is almost reaching these temperatures, not quite, indicates that the metals are softening in the way that we are expecting them to, which means that these models are working effectively. So our future plans for our research is we will continue evaluating our alloys in an on-Earth environment to make sure that they are working in the most effective way possible, that is, they are representing the alloys that we are working with to the most exact degree possible. Once we are absolutely confident in the fact that our alloys are accurately represented, we will transition them within the COMSOL model to a microgravity environment. We are not sure what we will see when they are put into a microgravity environment, but we are hoping to be able to catalog all the good and bad ways that the alloys may be behaving in a way contrary to what we are expecting. And once we have collected all of that information, we aim to publish in the future. These are references. Thank you so much for your time this evening. Are there any questions?
Yeah, we have a question from Skylar in the audience. She was wondering, what are some microstructural defects associated with friction stir welding, and would you expect these to be worse when manufactured in space?
We always have issues of the alloys not exactly fusing correctly. There tend to be bubbles or gaps that we encounter due to the quality of the weld that is formed. But the traditional form welding, the way people are trained, is with it being 9.81 like gravity. So they're very used to that, but putting it in a different area, the way the metal will move and bend could affect the overall quality, which will definitely affect the microstructure that forms and could potentially make the alloy weld weaker than what is expected.
In your background, you gave some information up until like 1984 when they did space welding, but there wasn't really a whole lot after that. Is there like a reason for that, and does that have like an effect on how you're researching?
I think it definitely does have an effect on our research, specifically because friction stir welded wasn't actually patented until 1991. So it wasn't even an option to be tested in space when they stopped testing welding in space. I think the primary reason why they stopped testing welding in space was with the completion of the ISS. They shifted more into answering the questions about being able to sustain life in space. Can plants grow in space? How long can humans live in space? What will the effects be? But now that we've answered a large majority of those questions and we're shifting more into deep space missions, we need to make sure that we not only understand how life reacts to deep space missions, but our materials and supplies as well, and how we're going to be able to maintain those. So this is sort of unknown territory for us, so I'm super excited to see what we find with this research.
Why are you evaluating the alloys in microgravity situations if friction stir welding doesn't form a weld pool?
So while friction stir welding doesn't form a weld pool like traditional welding, the two pieces of metal are still going through phase changes from solids into very viscous liquids. So they are still going to behave in a way that is definitely going to be affected by the gravity that they're in. So we need to make sure that we understand how they are exactly behaving if we want to be able to optimize the welds that we can form. So it's still important to make sure we understand that behavior.
In your presentation, you had like two very specific alloys that you were using. Do you have like reasons behind that, like why you chose those?
So we specifically chose aluminum 2219 because the COMSTOL program already had a model built specifically for the behavior of aluminum 2219 when it's being friction stir welded. So we're using that as a baseline. In addition, we're using both of them because aluminum 2219 and INCONEL 718 are both very prominently used alloys in the aerospace industry. At some point when we're on a deep space mission, something made up of both of those materials is going to break, and we're going to need to know how to fix them. That's not to say that we don't need to do all this research for every alloy that's going to be used, but this is more of a baseline for us to understand the process of how to measure the behavior of these alloys specifically. And then once we understand these, we can transition into testing more alloys as we go.